Um, I'm doing a sort of course online here. Right now, we're talking about using series solutions to solve differential equations. And I could put this piece of information on every one of my recordings. If you have any, if you want any other information, you may try emailing me. And here's my email address. Anyway, we were getting into, well, we already discussed power series solutions to differential equations. Now we're going to get into Frobenius series solutions. But before we go right into it, we have to talk about regular and irregular singular points. Remember, if it wasn't a singular point, it was an ordinary point, and there you could use a power series solution, power series to get solutions. Turns out we can sometimes, zero can be a singular point, but we can still get solutions. So we review this. This is the different type of differential equation we're solving. Here it is in standard form. We talked about that before. And these P's and Q's, after these any cancellations, will be, for us, it'll be ratios of polynomials over polynomials. So you'll have a numerator as a polynomial in X and a denominator as a polynomial in X. And we really get the singular points from these denominators. Since they're polynomials, they can be factored. And the roots of those denominators, all the roots of both of these denominators, P and Q, those are the singular points. Okay, we already knew that. Now we're going to distinguish regular and irregular singular points. These n's in the exponents mean some singular points could be repeated. This n is anything greater than 1, it's repeated. If this m, if this m is anything greater than 1, it's repeated. If it's repeated more than once in P, that is a irregular singular point. Whoops, what the heck happened there? If it's, whoops, if it's repeated more than twice in the denominator of Q, it is an irregular singular point. Any singular point that is not irregular is regular. And any point that is not singular is ordinary. So that's how you distinguish irregular from regular. How often it's repeated. More than once in P or more than twice. And here's the Frobenius theorem. If x sub 0 is a regular singular point, then there exists at least one non-zero solution called a Frobenius series. This looks an awful lot like power series, except for this factor of r here, or this extra factor of r, exponent. If it were a power series, this would only be non-negative integers. Frobenius series, the exponent can be anything. This is guaranteed to converge on the interval from 0 to r. Well, about your x sub 0. Remember, power series had a symmetric interval of convergence. So here's the, since we're going to center all r's at 0, we're going to make these x sub 0 zeros in our case. So here's what our Frobenius series is going to look like. Either one of these forms. And its radius of convergence is strictly 0 to r. So here's kind of a decision tree. Center everything at 0. 0 is an ordinary point. We're going to get two linearly independent power series solutions. This symmetric interval of convergence, minus r to r. R is the radius of convergence. If it's a regular singular point, we might get one or two. We'll talk more about this later. Frobenius series solutions. And this is the IC from 0 to r. If 0 is an irregular singular point, we're not guaranteed any linearly independent, any node series solutions, and we won't do anything further with that case. Here's some examples. So here's our differential equation. We can do some factoring. First, we do some factoring. So we could rewrite it like this. Then we'll divide through by this front term. Some things will cancel, like this x plus 3 cancels one of these x plus 3. So here's our p after cancellation. Here's our q after cancellation. So we can see that -3 and +3 are the singular points. Here, by the way, are the p and q written out for you. What are the irregular singular points? We're looking for anything higher to a power higher than 1 in p and to a power higher than 2 in q. Well, nothing's higher than power of 2 in q, so it doesn't contribute any irregular singular points. But this one is squared, so +3 is an irregular singular point. So the singular points are plus and -3, but -3 is regular, +3 is irregular. 0 is not a singular point, so we're going to get power series solutions. Radius of convergence is distance from 0 to 3, which is 3. There's our IC. Just characterized. Here's another example. Here's our ordinary differential equation. We'll factor this guy. Here's our P. Here's our Q. Remember, it's all of them combined, all the roots combined. Here the roots are plus or minus I2, and here the roots are plus or minus I2 and 0. So our singular points are 0 and plus or minus I2. Nothing is repeated at all, so all of them are singular. But in this case, 0 is a singular point, a regular singular point. We're guaranteed at least one Frobenius series solution centered at 0. Radius of convergence is, here's the closest singular point to 0. It's at a distance of 2 from 0 in the complex plane. So the radius of convergence is 2, the IC is from 0 to 2. And another example, the ODE, you can factor that front term, do some algebra. Here is P, here is Q, after all the cancellations and simplifications. So what are the singular points? 0, -1. Same here again, 0, 3, -1 again. 0, 3, -1. So those are the singular points, 0, 3, and -1. -1 from P, because it's repeated, is irregular. Everything in Q, there's nothing raised to a higher power than 2, so it doesn't add any irregularities. So 0 is a regular singular point, so we'll get Frobenius series centered at 0. What's the radius of convergence? What's closest singular point to 0? -1. So that dictates the radius of convergence. It's 1, distance from 0 to -1. So there's our IC, 0 to 1. So now that we know that, kind of how to characterize how to get started here. Once we start solving with Frobenius series, which is when 0 is a regular singular point. Here's what the Frobenius series is. This is by definition what a Frobenius series centered at 0 is. Why? So we'll take the first derivative and we get this. The second derivative and we get this. This, in this case, unlike the power series case, because we don't know what R is, we have to start these sums at n equals 0. Before we had just an n here, and when n equals 0, you got a 0. Now that's not the case. So these sums, as they appear up here, are what we're going to have to substitute into the equation. And we'll get into how to solve, how to go through this step by step in a subsequent